Especially in winter, much of the food we eat comes from thousands of miles away, often by airplane. Food destined for such long journeys must be produced and containerized for travel, a process that favors neither excellence of taste nor quality of nutrition. An enormous amount of fossil fuel is used in getting food to our tables. A gallon of jet fuel that costs $3 is the energy equivalent of about 2 person months of labor. The alternative is to produce food in cold months in greenhouses. Unhappily, conventional greenhouses like this hoop house require large quantities of non-renewable energy to keep their soil sufficiently warm for food production. Propane costs at least as much as gasoline and jet fuel. All come from crude oil that's in increasingly short supply. Thus, oil can be used for flying food over long distances or for keeping inefficient greenhouses from freezing plants. Neither option is consistent with long-term sustainability. And so that's the point of the R&D greenhouse, to experiment with some techniques for being able to grow in this climate and in related climates without having propane backup, and to be able to raise food all year round.
In the spring of 2008, the Colorado Department of Agriculture awarded a grant to the Cure Organic Farm and Synergistic Building Technologies to design, instrument, and test a research greenhouse. The key aim of the research is to investigate practical techniques for designing, building, operating, and controlling a new class of greenhouse capable of producing food all year around with minimal use of fossil fuel energy. The research greenhouse was built at the Cure Farm in eastern Boulder County. This video tells the story as of November 2010, first planting. A number of principles of building science have guided the design and construction of this research greenhouse. There is lots of insulation, both fixed and movable. There is plenty of thermal mass to ensure that the growing environment doesn't get too hot on summer days or too cold on winter nights. There are 24 south-facing windows that let lots of light in, but lose little energy when the sun sets because insulating shutters come to the rescue. There are many reflective surfaces, both inside and out, that help direct solar light to both soil and plants. There are 5 ventilation techniques that control air temperature, carbon dioxide, and moisture while minimizing energy waste. And there are several monitoring and control schemes to help learn what works best to optimize the growth of fresh organic vegetables. Grail coat has several happy properties that make it especially useful for greenhouses. It is highly flexible, so resists cracking over many years. Second, unlike ordinary stucco, it is sufficiently water resistant that it may be used around foundation walls. Further, it sticks to OSB, rigid insulation, and even steel. So we used it extensively, even on the super efficient doors we made from OSB and polyisocyanurate, a first according to the manufacturer.
So in short, this is a super insulated structure, and it's very tight, and that's part of the genius of it. So what glass we have is modest, but has a high solar heat gain coefficient, and it's also protected by insulating shutters as soon as the gazaudas, due to temperature difference, are higher than the gazindas due to the sunshine coming in. We'll see about that in a second. So you're watching a pocket shutter. The insulating polyisocyanurate that's 2 inches thick has an R value of rated at 13, and it lives up behind that green part of the shutter, which has got a 1/2 inch of polyiso inside and out, and then on the inside of that whole section is another 5.5 inches worth of cellulose, which is R3.8 per inch. So when that shutter is within the pocket, the R value of that is a substantial number, 35 or 40. And when it's not between the pocket, that portion of it up there is well above 30. It's pretty much its own space. And I think what this does is maximize the likelihood of having real good R values day and night to do it the best we possibly can while maximizing the amount of light that comes through. You'll notice everything is white, and then further, once it gets inside, it bounces off of all of the white surfaces. Everything on the inside is highly reflective, on the order of 95 to 98%. And what then happens is that light wanders around until it hits on a surface where it's absorbed, and that's typically the plants themselves or else the dirt. All of that's good. That's what we want to happen. So that maximizes the likelihood of good things happening to solar coming into this place while minimizing the amount of absolute glazing that we have to have so that the losses are tinier. And then when there is no sun to be gained, then we make the losses substantially smaller by virtue of the insulating shutters.
The Greenhouse Earth Thermal Storage System, we call it GETS, is inspired by Chinese greenhouse technology. The idea is to take warm, moist air that gathers at the top of the greenhouse on sunny days and pipe it below the surface of the soil, where it is cooled and dried by distributing heat and moisture near the roots of the plants. The cool, drier air that emerges at plant level is welcome on hot afternoons, and the warm, moist soil is welcome on cold nights. The GETS system pulls warm air from the top of the greenhouse via a variable speed 12-volt DC motor that powers a squirrel cage blower that moves air at over 200 cubic feet per minute. A plenum that began life as a trash basket made of recycled PVC plastic distributes the air to 8 4-inch diameter drainage pipes that average 50 feet in length. The pipes are buried from 1.5 to 3 feet deep and are laced with holes to facilitate the movement of air and moisture. The pipes are covered with loose nylon socks to impede the flow of both small creatures and dirt. At the far end of the greenhouse, they are connected to solid PVC pipes that direct air back above ground. Screens on each pipe keep rodents from making the GETS system their home. As a result, the greenhouse is kept from getting too hot during the day since warm, moist air is cooled by the soil. In turn, the soil is both heated and moistened, thereby diminishing the effects of cold nights. Through measuring temperature and humidity at key points, we hope to automate control settings to optimize growth in all seasons.
The sun goes down and the temperature difference between inside and outside goes up, and that's when we want to move these things from being roughly R1 to roughly R12. And that's why this greenhouse is going to work real well all winter long.
This plot of temperatures over a typical 24-hour period in December sheds light on the differences between the performance of the energy-efficient research greenhouse and the hoop house 200 feet away. The bottom curve shows outdoor air temperature over the period with a low of 25 degrees Fahrenheit and a high of 40, a diurnal swing of 15 degrees. The hoop house plot has roughly the same shape as the outdoor air temperature profile, but its swing is a full 33 degrees. The hoop house indoor air temperature is below freezing for half of the period. The research greenhouse swings only 6 degrees and has a low of 59. Most important, the environment in the research greenhouse promotes excellent growth even in the short days of winter close to the winter solstice. This picture shows the growth of radishes 10 days after planting seeds, just 2 days before Thanksgiving. Ann Cure observes that the plants are currently growing at a pace usually only seen in June and July if there is plenty of water and lots of sunshine. 16 days after planting seeds, this is what the plants look like on a December day, only 9 hours and 24 minutes long. Note the tomato plants on either side of the row of radishes and arugula near the north wall on the right. Sweet peppers, eggplants, basils, cucumbers, and summer squash are in the center row. The row closest to the south-facing windows includes sprouts of salad mix, rainbow chard, carrots, and melons. We believe that this is indeed the dawn of a new age in greenhouse design. The team is already examining a second generation of insulating shutters This one has a single pocket that stores 2 shutters when not needed, then moves them between 2 sets of glazings when the sun goes down. Such movable insulation, combined with other principles of efficient greenhouse design explored in the present project, is resulting in a range of exciting new greenhouse designs. This greenhouse is designed to be attached to the south facade of an existing home. It is super insulated and coupled to the earth, but its north wall is part of the home to which it is attached. In addition to providing fresh food a few steps from the kitchen, it supplies the home with passive solar heat and fresh oxygen from growing plants. Nighttime losses are tiny, so the home never has to provide heat for the plants, although carbon dioxide is welcome. Lots of variations on the theme of providing healthy local food throughout the year are in the green pipeline. Many thanks to the Colorado Department of Agriculture for helping to make it happen sustainably.